So we talked about routing protocols, and in this video, we're going to give you an overview of RIP, or the Router Information Protocol, and then we're going to go set it up on a small lab. So, as I've mentioned, RIP is the Routing Information Protocol. It's one of the older routing protocols out there. It was defined in RFC 1058 in June of 1988. I remember 1988. I was in middle school. I suddenly feel very old. But nonetheless, there are older routing protocols, but this is one of the first, and it is still one of the most widely supported. There's not hardly a network device out there that doesn't support RIP in some form or fashion. RIP is a distance vector routing protocol, or as I like to call it, it's routing by rumor. Basically, this means that every 30 seconds it sends its entire routing table to every connected neighbor, and it sends this out on a UDP multicast address, so that anyone that's listening to that multicast address will get the route table update from the routers that are broadcasting it. The neighbor, or the router that received the broadcast or the multicast, accepts this update, puts it in its routing table, and rebroadcasts out that combined routing table to all of its neighbors. So you'll recall when we talked about convergence, you can see how RIP has a very high convergence time because every router in your network requires 30 seconds to realize that one of its neighbors has sent it an update for a network that no longer exists. So there are some limitations of RIP, which is why it's not really used on big networks. RIP version 1 did not use the CIDR net masks. It only advertised on classful network boundaries, and RIP version 2 fixed this. You'll see this when we go into our lab and we don't turn off auto-summarization. You'll see that our networks get broadcast out with the standard default net mask. In our case, we're using a 10. Network, so you'll see it broadcast 10.0.0.0/8. This is fixed in RIP version 2, but you have to specifically turn off auto-summarization for this fix to work. Another limitation is that it does not take into account link speed, it only uses hop count. And this is a symptom, or a feature, if you will, of it being a distance vector routing protocol. And again, I've mentioned it when we talked about routing protocols in general, but the distance vector routing protocol, if it sees a route that is directly connected or is only one hop away, it'll send all of the traffic for that network through that one hop, regardless of whether that happens to be a dial-up modem. It doesn't care. This is closer, so this is where it goes for that network. Also, and the big limitation for corporate networks or large enterprise networks, is RIP has a maximum of 15 hops. In other words, you cannot cross more than 15 routers. In fact, if RIP sees a network that is advertised as having a metric of 16 hops, RIP automatically marks that route as being unavailable and unreachable, and just don't ever send any routes this way. So let's move on and let's look at our little diagram. You know how I like diagrams here. So we have 3 networks here connected with 3 RIP routers. 172.16.1, 2, and 3, and these routers are the .1 routers. So if we turn on RIP on all 3 of these routers, then these routers begin to advertise the networks that's locally connected. It also begins to advertise these point-to-point links, but we'll just ignore those for the time being. It makes our graphics simpler here. So this router here advertises 172.16.2.0 to this router and this router. It's basically saying, hey, I know how to get to this network. It's directly connected. This router here advertises 172.16.3.0 and 172.16.2.0 to this 172.16.1.1 router over here on the left. So essentially what happens is this router over here gets this 172.16.2.0 network advertisement from 2 different routers. It gets it from this router here and this one here on the bottom. The metric that it receives from this router is 1. This has a metric of 2. And since RIP only cares about hop count, then this router knows if I want to reach 172.16.2.0/24, I will send it out this link. Even if this link happens to be an ISDN or a dial-up modem or satellite or something that's just really there for backup purposes, because it's only one hop away, it will always go out this link. If this link were to fail, then this router would realize it after about 60 seconds and go, oh, well, this link's failed. I need to send my traffic out this direction. The same thing is happening with these routers as well. For example, this 172.16.3.1 router is receiving the 172.16.1.0 advertisement from this router as well as the one on top. And this is where that routing protocol logic comes in, where it realizes that I have multiple paths to this network. Which one has the best metric? And honestly, playing around with RIP is a good way to learn about dynamic routing protocols. You don't have any of the complexity that you get with OSPF or EIGRP. You don't have to worry about autonomous system numbers and summarization and stub areas and all that other wonderful stuff you get with the link state routing protocols and with the hybrid protocols. RIP, you just turn it on and you watch the advertisements fly, and you can actually debug RIP on the router, and you can see the advertisements come into the router from its neighbors. So with this, we actually encourage you, do try this at home, because you're really not going to break anything, especially if it's a lab. That concludes our overview of RIP.